3/17, St. Patrick's Day, right?
Yep.
All
News
right.
to me.
Yeah, that's what I thought. I don't even have my green on. Somebody could pinch me. Isn't that how it goes? If you don't have your green on, you get pinched and you can't drink the green beer or something. I don't know.
Yeah, you usually get pinched.
Yeah, that's what my grandmother always did. She claimed she was Irish and she'd pinch you if you didn't have your green on. I don't know how Irish she really was, but she always claimed she was. Okay, guys, I got 3:30, so let's go ahead and get started. So any questions, concerns, thoughts about lab yesterday? I thought it went fine. Think the kombucha behaved pretty much for everybody. Of course, looking back on it now, we probably could have gotten everybody through both experiments in a single night, but that's okay. You live and you learn. So that way we didn't have to rush. So next week, we're just going to swap. So if you had the pH meter this week, you're going to do the 4 indicator titrations. If you had the indicator titrations, you'll use the pH meter next week. So that's how we'll go. All right, so a few things moving forward here. I just wanted to talk a little bit about the actual analysis reaction a little bit. So just a little bit of background on kombucha. I'm just kind of making this up as I go. I don't know how much you guys know about it. I know some of you guys do know about it. You know, I know Andrew makes his own. He's got a Scobie hotel, so he's making his own kombucha. And I know some of you guys drink it, so you know a little bit about it. Basically, you know, the idea is people like it because it's a probiotic, like yogurt. So it has gut healthy bacteria in it. So supposedly when you drink it, you're populating your intestines and all that good stuff with healthy bacteria. Basically help you digest food and keep you healthy down there. So that's the basic idea. People use it as a health drink. I don't know how, you know, effective it really is in that effect. I don't know if there have been that many studies done on it. I just think it tastes good. I just like it. It's refreshing. It's a little bit bubbly, a little bit sweet, a little bit tart. So, you know, I just think it's kind of a nice little drink. So I actually, drink basically a boatload of kombucha. But anyway, what it really is it's a fermented tea-based drink. So it's fermented. Okay. As I mentioned, it's also a probiotic. So what that means is it contains so-called healthy bacteria. Gut healthy bacteria. Okay. So that's what a probiotic is. That's why people, for example, eat yogurt and other sorts of things like that. There's all sorts of other probiotic foods you can get or drinks that you can get as well. But kombucha is just kind of an interesting one right now to me. All right. So the basic idea here is, you guys familiar with the idea of fermentation? So that's basically where we take something like sugar. So if you're actually brewing kombucha, what you start with is essentially tea, and you add sugar to it. Now to that, you add this thing called a SCOBY. And what SCOBY stands for is it's a symbiotic colony of bacteria and yeast. Okay, so basically you've got both bacteria living in there and yeast living in there. And it's the bacteria, or rather the yeast, that are going to allow for the fermentation to happen, right? So, you know, when you think about brewing beer, for example, that's fermentation. So in the case of kombucha, what's happening here is the fermentation process is converting we'll put yeast down here, and it's a particular type of yeast. It's not the same kind of yeast that's used in beer brewing, but yeast is basically yeast. Basically what happens is the sugar gets broken down by the yeast, and you end up making ethanol. Okay, so that's ethyl alcohol. That's the kind you drink. Okay, now what ends up happening here is that the ethanol doesn't just end up staying in the kombucha, it gets used up by the bacteria. So the ethanol becomes food for the bacteria. So you can imagine a bunch of drunk bacteria running around, right? And what you get out of this is organic acid. And CO2. Okay, so that's one of the reasons that the kombucha is actually a little bit fizzy, is you end up getting some natural carbonation from the carbon dioxide. Now, the important thing for us is the organic acid. That's the important product. Okay, so it turns out, depending upon what bacteria you've got in there and how they're operating and what kind of sugar you've got, basically end up with two types of organic acid. So what ends up happening in the case of the sugar during the fermentation process is the sugar actually gets cleaved, that sucrose. It gets cleaved into two simple sugars, glucose and fructose. So basically, if you have the glucose, when the bacteria break that down, what you get from the glucose is going to be gluconic acid. Okay, and that's a weak acid. You can probably find a Ka for it actually in your table there. The other simple sugar that you get from the breakdown of the sucrose, just the table sugar, is you get fructose. And then when the bacteria do their thing on the fructose, what you actually end up getting is acetic acid. And it turns out this is the more favored process. So what you'd ultimately expect to see in a kombucha sample is going to be a relatively high concentration of acetic acid relative to the gluconic acid. Okay, so when you study the acidity of kombucha, the primary acid you're probably going to be looking at is acetic acid. Okay, and that's kind of the standard weak acid that we've been talking about all along. So that's what HC2H3O2. So there's probably going to be some gluconic acid in there as well, but we're going to ignore it because it's going to be a minor component. Okay, it's going to probably show up in there in one way, shape, or form in your titration curve. But the big increase that you're going to see in the pH as you titrate with the base is going to be due to the neutralization of the acetic acid. At least in all the ones Dr. Kagris and I did, that's what we end up seeing. All right, so that's what we're after. That's our analyte in this case. So any questions about what kombucha is and kind of where the various things come from, or anything else you want to know about it at this point?
Well, I was wondering, thinking about the lab yesterday, so if it's fine enough, it probably won't be that big of a difference, but within a week's time, wouldn't the acidity level technically rise, but it might be really small that we couldn't measure it?
Yeah, that's actually a really good question. So like from 1 week to the next, given that it's a live beverage, if you have kombucha sitting out at room temperature or even in the refrigerator, yeah, it's going to continue to actually work. Now, eventually all this stuff's going to come to some sort of an equilibrium, right? And that's actually what happens, because when you brew kombucha, I mean, Andrew, how long would you normally brew kombucha like when you do it? It's generally over several weeks, right?
Well, it depends on how strong the SCOBY is, but for me, it's only about a week and then another week for the secondary fermentation. So in total, about 2 weeks.
About 2 weeks with your primary and secondary.
Yeah.
And what Andrew's talking about there is normally we do a primary fermentation, which is just sugar and tea. And then we might want to add, for example, a flavoring, which might be a fruit flavoring, or we might want to add spices or something else to the kombucha at that point, or maybe a little more sugar or something. Something that maybe just changes the flavor palette a little bit. So then we add those things and let the fermentation continue for another period of time. So that's called a secondary fermentation. Okay, so that's a normal thing kombucha brewers do. But yeah, generally, when you're talking about brewing kombucha, you're talking about letting it go for maybe 2-3 weeks. Again, depending upon how sweet you want it versus how acidic you want it. So if you want a sweeter kombucha, you'd probably have a shorter brewing time. And if you want a more acidic tartar kombucha, you'd probably have a longer brewing time. So in other words, what you're trying to do is balance out the residual sugar versus the acetic acid that you're making. Because remember, the acetic acid gives it that sort of tart sour flavor. So some people like tart kombucha, some people like sweet kombucha. So the brewing time is a big factor there in terms of defining what kind of kombucha you're going to end up with, as well as the secondary flavorings that you might add. Okay, but yeah, the original question was, what happens if I leave it sitting for a week? Because like we analyzed the kombucha sample this week and then it's going to sit for 7 days and we're going to use it again next week, right? So that's kind of the question that got asked. So wouldn't the composition change a little bit? Is that the correct question?
Yeah.
Yeah, that was what you're getting at. So here's what I did. As soon as you guys were done with it yesterday, Kim and I took the samples and we put them in the freezer in the organic lab. So basically, if we freeze it, we're basically temporarily shutting down the yeast and the bacteria so that they can't really do their thing. So essentially what we have is a snapshot in time of what the kombucha looked like when we put it away. And then we'll thaw it again next Tuesday. So ideally, since the bugs can't do their thing, the composition of the kombucha technically shouldn't change between now and then. Now, if I just left it in the fridge or if I left it sitting out on the bench top, yeah, it would continue to grow. And as a matter of fact, if I left it out that long, I might even start to see sort of a solid SCOBY forming out on top. Okay, I've actually done that. If you just leave kombucha sitting out at room temperature, just the kind you drink, the bugs in there will actually generate this thing that kind of looks like a mushroom cap on top. And that's the SCOBY that we're talking about, that Andrew refers to as keeping in his SCOBY hotel. And that's a place where the yeast and the bacteria can reside and be healthy. So, a lot of times when you're brewing a new kombucha, you might take an old SCOBY and throw it on top or inside of it or something like that to reintroduce or inoculate the new solution with the microbes that you need. Okay, so yeah, that's a good question. But anyway, let's focus here on the acetic acid because that's the analyte that we're really after in this titration, because that's going to be the primary organic acid that's going to be formed in the fermentation of the kombucha. So here's the reaction. We've got the HC2H3O2. And I'm going to let that react with the standardized hydroxide. So I'm just doing this in terms of a net ionic equation here just to keep things simple. Now, if in this case, obviously the acid is going to be the acetic acid and the hydroxide is going to be the base, okay, we can predict what two products we're going to make. It's just going to be a Bronsted-Lowry acid-base reaction, very similar to the KHP reaction we were talking about last time. But this one's simpler, because acetic acid is a monoprotic acid. It only has one proton it can give up. So we're going to make water. And we're going to be left with the conjugate base of the acid, which is the acetate. All right. So there we go. There's the conjugate base, and water would be the conjugate acid in this case. So if I wanted to come up with a K for this thing, this is kind of the same issue we had with the KHP, where we look at that and we see that we have a strong base reacting with a weak acid. So that doesn't look like any kind of K that we've seen before. Because when we talk about KAs and KBs, it's always an acid or a base reacting with water, right? Water is always on the left-hand side. So if you look at this reaction and you kind of go backwards with it, and you look at it going from right to left, that's something you kind of identify, right? If water's the acid and the acetate's the base, look what you're making. Hydroxide and the original acid back again, right? So if you looked at the reaction in reverse, what's the K for the reverse reaction? What kind of a K is that? What will we call that?
It's the inverse of the Ka, or
Well, you're kind of close. It looks like what? A Ka, a Kb, a Kw. Of those three, what are you looking at there?
Kb.
Kb, yeah. It's the Kb for the acetate ion. Right? Now, if we wanted to, we could actually calculate that, couldn't we? Now, you can't find it in the table. We know how to calculate it. We can calculate it from the Ka for the conjugate acid, which is the acetic acid. Okay, so if I wanted to know the Kb for that, I know that Ka times Kb is equal to Kw for any conjugate acid-base pair, right? And I want the Kb. So that's going to equal to the KW divided by the Ka that I look up for acetic acid. So KW is what, 1.0 times 10 to the minus 14th. Remind me of what the Ka for acetic acid is. I want to say it's like 1.75 or 1.8. We'll call it 1.8 times 10 to the minus 5th. Does that sound about right, guys? We've used that one before, but I think it's right around there. So if you calculate that KB, what do you get? I don't have a calculator on me. Hopefully one of you guys do. Looks like it's gonna be somewhere around 10 to the minus 9th.
Uh, 5.5 rounding up to 6 times 10 to the negative 10th.
Okay, sounds about right. 5.6 times 10 to the minus 10. Fair enough. All right, so now if you look at that, for the reaction that I've actually got there, what's the K for that reaction in terms of the KB? What is it? So my K for my reaction is equal to what? How would I couch that in terms of the KB I just derived?
It's the inverse of the KB, not the Ka.
Aha, sure thing. 1 over the KB in this case, right? It's 1 over the KB, because remember the KB reaction is the reaction I've got going from the right-hand side to the left-hand side. So if I flip it, right, I have to take 1 over it. That's what the rule is when we manipulate these reaction equations. All right, so now I've got 1 over some really small number, which is like 5.6 times 10 to the minus 10th. And you know what I'm going to ask you to do next is get me that value just so you guys can see what it is.
Uh, 17 followed by a bunch of 9s. So 1, 7, like 9,
So it's going
9.
to be like 1.8 times 10 to the times 10 to the minus something, or 10 to the something.
It's to the 9th.
Yeah, that sounds about right. Okay, so the point is, it's really huge, right? It's really huge. So what do I assume about a reaction when the equilibrium constant is that big? What assumption can we make? We did this when we talked about precipitates, right?
If
the
product.
That we're going to make 100% product, right? So I'm going to make the assumption, since the K is really huge, that this reaction, for all intents and purposes, in other words, our ability to measure product versus reactant goes 100% to the right. It's a limiting reactant problem at this point, right? And that's what we can do. So remember, this kind of summarizes that little rule I gave you at the end of class in a very rushed fashion last time. And that's why I kind of wanted to do it again for the acetic acid, so you guys could see it again. But here's the rule. So we'll just re-summarize it. Weak plus strong goes 100% to the right. So in other words, if you go back and look at my original reaction, do I have a weak acid there? Yeah. My acetic acid's a weak acid. Do I have a strong base? Yeah, hydroxide's a strong base. So I've got a weak plus a strong, and now I can assume it goes 100% because it has this really huge K value associated with it. So we just proved that again. Okay. Any questions about that? And that's, again, just kind of revisiting the very same concept that we finished up class with last time. And we're going to use that again and again. As a matter of fact, when you get to this kind of stuff in dynamics, you're going to use it there. So this little rule of thumb of weak plus strong goes 100% to product is definitely worth remembering. It's a nice little shortcut you can use. All right, so that being the case, let's talk a little bit about titration curves. So we would get these using a pH meter. And the idea here is that we're going to plot the pH as a function of the volume of the titrant added. Okay, so this is actually the first kind of plot that you're going to make using the data that you get or you already have. Okay, so I think your lab directs you to do that. So let's think about what this thing would actually look like. So we're plotting pH here. And we're going to plot this versus the volume of the hydroxide ion concentration, or rather the volume of the hydroxide that we add. So that would typically be in milliliters, right? And pH is unitless because it's a log quantity. All right, so we're starting out with kombucha. Now, you guys made some initial measurements, and also based on what we just said about kombucha, would you expect kombucha to be acidic or basic?
Acidic.
Yeah, and you guys measured that, right? So you dropped your pH electrode into your diluted kombucha solution, and you probably got a pH around, 3.5, 4.5, 5, somewhere in there. Okay, so the pH is going to be less than 7. So, if we just kind of say we got a pH of 7 here at the midpoint, what would we actually see? Well, we might actually see an initial pH somewhere down here for our kombucha. Okay, so what's going to happen? Well, as we add the acid, rather we add the base to the kombucha, we're going to start to neutralize it, right? So presumably it's acetic acid, right? So we're going to start to neutralize that acetic acid. So as we neutralize the acetic acid, what do you expect the pH to do? Go up, go down, or stay the same? Yeah, you're adding a base. Okay, so you're chewing up that acid, so you'd expect the pH to start to increase. So it starts out kind of flat, and maybe does something like this. And then you're going to get to some point where you're going to see a really big increase. And then what's going to happen is it's going to then start to level off again like this. Okay, so this is what a typical pH titration curve would look like when we're titrating a weak acid with a strong base. And that's exactly what's happening here. So again, we'll just remind ourselves of what we got. It's going to be CH2H3O2 plus hydroxide, right? And you guys know where that goes. So that's the reaction that's actually happening. The hydroxide here, of course, is going to be the titrant. That's what's in the burette. Okay. So that's what we see. That's what the pH meter is going to tell you. So that's a plot you're going to make. And hopefully it'll look something kind of like that. Okay. And now from that plot, you're actually asked, and I'm not going to tell you how to do it, but you're essentially asked to back calculate a Ka for acetic acid. Okay, so you're going to end up getting some values from the plot that you're going to stick into an ice table. Okay, and then you're going to be able to back out a Ka from that. So that's an exercise that we ask you to do in there. Okay, so that's where that plot's going to come in useful. Now, normally, if we want to get, and what's the point of a titration, right? It's to get to an equivalence point, right? Where the moles of the acid are equal to the moles of the base. Because ultimately, what is it we're trying to do here? We're trying to get the concentration of the acetic acid. That's what we want, right? How much dissolved acetic acid is in the kombucha? That's what we're after. Okay. So, how would I do that from this plot? Well, the way I would do it by looking at this plot alone is I would look for the inflection point in that high rising part of the curve. See the curve where the slope is the biggest? The inflection point is the point where the slope is the largest. So I could kind of sort of eyeball that. So one of the things we kind of ask you to do maybe is once you've got this, sort of draw, a curve through it and kind of not really connect the dots, but just make sort of a smooth curve through the data like this. I think that's what we kind of asked you to do. And then what I would do is I would look for the inflection point. That would be the point of steepest slope on the curve. So it's kind of hard to sort of figure that out, but it might be somewhere typically sort of in the middle of the curve. So if you're looking for like an inflection point, it might be somewhere like that. So then what you might do is you might drop down a vertical line here and find out where it hits that x-axis. Now, where it hits the x-axis, that's what we call an equivalence volume. And it's called that because that's the volume of titrant required to get to the equivalence point in the titration where the moles of the acid are equal to the moles of the base. Okay. Now, once I have the equivalence volume and I know the concentration of the base, remember volume times molarity gives me moles. And then I can use my mole bridge to go from the hydroxide back to the acetic acid, and that gives me the moles of acetic acid. And then if I knew the original volume of the kombucha I put in there, right, and you measured that out with a microburette, then you can convert that to a molarity. So that would give you the molarity of the dissolved acid in there. Okay, so that's how you would actually use that plot to do it. But why is this not the best way to go? Well, the main reason this is not the best way to go is because it's kind of hard to find that inflection point on the curve. Okay, because there could be kind of a variation of range in there across the y-axis where it kind of looks like the curve has about the same slope, doesn't it? So it's really hard to pick out that point where the slope is the largest. And there's some things you can do. I mean, some people will kind of draw lines through these things like this and a line through here like this and try to find a midpoint and all that kind of stuff. You know, so there's ways to do it, but it's still going to be a little bit dicey to determine that equivalence volume from this kind of plot. Okay, so how do we get around that? Well, what we do is we try to home in on that equivalence volume, that inflection point, by generating what's called a first derivative plot. So basically what we're going to do is we're going to literally take the first derivative of the pH titration plot that I just showed you. Okay, now you guys might remember from calculus, if you have a curve that looks like the one I just drew and it has an inflection point or point of greatest slope, if you take a first derivative of a plot that looks like that, you know what it ends up looking like? Anybody remember? See how much you remember your calculus.
I don't remember.
Well, it actually ends up looking like a peak, almost like a Gaussian peak. And you can kind of see that because when you take a first derivative, what does a first derivative do? Well, it's basically looking for a minimum or a maximum of slope, right? So basically, what is an inflection point? Well, it's a maximum of slope. So when you take a first derivative, what you're really going to see is in the front end of that, you know, what's going to happen is the peak is going to increase up to the inflection point. And then once we pass the inflection point, look what happens. The slope of the curve decreases again. So now it crawls back down the other side and you get something that almost looks like a Gaussian peak. Okay, so basically you get a peak. And it's a lot easier to find the top of a peak than it is to try to find an inflection point in a curve like the one I just drew for you. So essentially the first derivative plot really helps us to home in on where that inflection point really is that we're going to then use to determine an equivalence volume. So how do we make a first derivative plot? Well, it's going to be based on the same pH and volume data that we have already acquired. And there's an example of it in your lab, but let's just go ahead and just take a look at it. So what have you got? You've got pH data. You've got volume data in mils. Okay, so this is data you will have acquired with your meter. So let's say your pH is 12 point. I'm just going to have one that goes the other way. We'll say 12.26, 12.03. Doesn't matter which way it goes. The math is the same. This is for an old titration that we did where we actually went in the opposite direction. Doesn't matter. The math works the same way. And 11.53, let's say, just because I have these numbers worked out. Here's the volumes. We did this with a macro burette. So this was at the 0.00. Then we added a little bit of titrant and the pH went down. So we added 0.15 milliliters. The third one was 0.26. So you can see what's happening in this particular titration. This one corresponded to 0.31. As I'm adding more titrant, in this case, the titrant's going to be an acid, right? And it's driving the pH of the solution down because whatever the analyte solution is actually a base in this case. So it's the opposite direction as that you guys are going. All right, so next thing we do is we have to get an average volume. So I'm going to call that a V average. That's also going to be in mils. Okay, And it's basically going to be the combination of two data points. So what I'm going to do is I'm going to get the average of that volume and that volume, that volume and that volume and that volume and that volume. So how do you calculate an average between 0 and 0.15? How would I do it?
Divide 0.15 by 2.
Yeah, so you take 0, add it to 0.15 and divide by 2. And when you do that, you end up getting 0.075. Okay. So what's the next one we want to do? What's the average between 0.15 and 0.26? So you guys know how to do that. You add up 0.15 and 0.26 and divide by what?
2.
2. Yeah, same thing. When you do that, and you can verify these values, you get 0.205. Okay. Then you can do the very same thing for the next set of data. You've got 0.26 and 0.31. You add them up, divide by 2, you get 0.285. Okay. So that becomes, in our first derivative plot, this becomes my x-axis. All right. So now there's another thing that we have to get. I need to get the delta pH. And normally we would just do this as an absolute value. In your case, it's going in the correct direction, so you don't have to worry about changing the sign on it. But in my case, the delta pH would be, it's always a final minus an initial, right? So it's 12.03 minus 12.26. And if I take the absolute value of that, I get 0.23. Okay, so everybody see I'm working with the pH values now. So then for the next one, what would I do? I would take 11.71 and subtract 12.03 from it. And what do you get when you do that? You get like 0.32. See, I'm just kind of working my way down the list here the very same way. Then for the last one, what would I do? I would take 11.53 minus 11.71, take the absolute value, and you end up getting 0.18. Okay. So this one, so this is, for example, number 1, number 2, number 3, and this one's number 4. So what would this actually be if I were actually doing it? This would be pH 4 minus pH 3. Okay, everybody see how I did that? And then take the absolute value of it. And then the other thing I need is a delta volume. And that's going to be in milliliters. So how would I calculate a delta volume?
Final minus initial volume.
Final minus initial. So for 2 minus 1, it would just be 0.15, wouldn't it? And then for the next one would be 0.26 minus 0.15. That's what, 0.11. And then for the next set, it would be 0.31 minus 0.26. That's what, 0.05. Okay, so this one, just to give you an example, would be V4 minus V3. Okay, so now I've got everything I need to produce my first derivative plot. Now, here's the thing. What's the y-axis on a first derivative plot? Well, what I'm going to do is I'm going to combine these values at each one of my points. So the y-axis is actually going to be, if I can spell, it's going to be the ratio of delta pH over delta volume. So that's going to be my y-axis. So now, if my x-axis is my average volume and my y-axis turns out to be the ratio of delta pH over delta volume, what I'm going to end up with is something that's going to look sort of like this. Okay, so this is going to be a delta pH over a delta V. And the units on that would be what? Inverse milliliters. And I'm going to plot that versus V average. And that's going to be in terms of milliliters of my titrant. Okay, that's going to be obviously hydroxide. Okay, so now what you're going to end up getting, and again, it's going to kind of stem from the plot, the pH plot that I gave you up here where I plotted pH versus the volume of the titrant. Okay, now what we're going to see is something that looks like this. So I'm going to have data that's going to maybe crawl along a little bit, but look kind of flat for a while. Why? Well, because we're kind of in the flat part of the curve here where the pH isn't changing very much with respect to volume, right? Because remember, when we calculate a first derivative, we're calculating a slope, right? It's a rise over a run at any given point. Okay. And then what's going to happen? Well, at some point now, you see the slope in my pH plot start to increase. So now what's going to happen is I'm going to start to see an increase in my data. And then I'm going to hit the inflection point, and now I'm going to start to see the slope drop off again. And what I'm going to get now is something that looks sort of like this. And then notice how the curve flattens up on the top. When it flattens up on the top, it gets flat again here because the slope starts to approach zero again. Okay, so your first derivative plot's going to look sort of like that. All right. Now, here's what I ask you to do. There's a lot of kind of useless information in the first derivative plot. So, for example, we don't really need these flat regions. So one thing I kind of ask you to do in there is to maybe take a certain region of the first derivative plot and blow it up. So you can kind of get rid of all the data to the left and the right of those lines and sort of recast this so it blows the first derivative plot up so I can really actually see what's going on there. And then in the blown up plot, what we normally do is this. Now, Dr. Kagris actually wrote the procedure for that part of it. And he says to draw an arc through this. And I think by that, he means just kind of a curve. What I normally have you do is kind of take a ruler, for example, and draw a best fit line through the rising data and extend it on up like that. Then I'm going to have you draw a best fit line through the falling data. Okay, so that might look something like that. And what you're going to make is something that kind of looks like a TP, right? So now what you do to get your equivalence volume is you're going to go to the top of the TP where the two lines cross each other and intersect. And now you're going to drop that vertical line down to the x-axis. And right there where it hits or kisses the x-axis is your equivalence volume. Okay, that's the volume you want to pick off. Okay, now notice that it may not actually correspond to an actual point on the plot. It's just wherever those two lines cross each other. Okay. And again, another advantage of blowing up the x-axis a little bit by eliminating that data on either side of the TP, if you will, is that now I can actually end up getting tick marks down here that end up giving me enough sig figs to correspond with what the burette was giving you. Okay, so in other words, your burette goes to what, the thousandths place, is that right?
Correct.
So each one of those ticks, if you actually work it out right, should be good to the nearest hundredth. And then when you drop that line down, you can guesstimate to the nearest thousandth. So you kind of want to set this up so that you've got a stretched out enough x-axis so that you can set your tick marks to the nearest hundredth of a milliliter. Okay, so we can actually put that in there. So plus or minus 0.01 mil per tick. Okay, so then, if it falls between two, you can guesstimate to the thousandths place. So you don't end up losing a sig fig. Everybody see what I mean by that? You want this plot to give you the same significance or precision that your burette would. All right, any questions so far about this, guys? Does that kind of make sense in terms of how we actually come up with a first derivative plot and what it's actually telling us?
Yeah.
Okay, so hopefully that clarifies, because I know a couple of you guys asked me about it in lab yesterday, and like I said, Dr. Kagris gave some example data in there. So, you can kind of follow what I did here and then hopefully look at his data and be able to reproduce that. And then that shows you how you're going to cast your own data to make both of these plots. So you're going to make the first plot and you're also going to make the second plot. Okay. So that's how we do it. All right. Any other questions about that? Everybody good? All right, so we have a few minutes left. So that pretty much covers everything I wanted to cover about, how to deal with the data from the dissolved acids lab for the kombucha. Now, it doesn't really finish what I need to do with acids and bases because, hey, we got another week of lab, which means that, hey, we've got a few more days to actually talk about acids and bases before we move on into the next lab. And by the way, the next lab is still going to be kombucha, and I think I'm going to use the same samples. But the next lab is actually going to involve, just to give you an idea, go back to your kombucha up here that we talked about. We're going to focus on the ethanol in the kombucha. So if you're in the kombucha industry, okay, and you realize that it's a fermented beverage and you're making ethyl alcohol, right, which is the kind you find in, beer, wine, liquor, all that good stuff, you run the risk of asking yourself, okay, is the kombucha that I'm selling really non-alcoholic? Okay, because there's always going to be some residual ethanol in there, just like there's some residual sugar in there. And it turns out for a beverage to be considered non-alcoholic, it has to have less than 0.5% volume to volume ethanol in it. Okay. If that percentage by volume goes above 0.5%, then it's considered to be an alcoholic beverage, and it has to actually be marketed as such. So you can't sell it to minors, and technically it has to be taxed differently. Okay. So this is a big deal to kombucha manufacturers, and a lot of them are very concerned if they're selling non-alcoholic kombucha, whether or not their kombucha is really less than 0.5% by volume in ethanol. Okay, so you can see this is like a huge issue. And as a matter of fact, there have been some fairly major brand kombuchas that you can buy in the grocery store that were actually dropped by grocery stores a few years ago because it turns out that people were spot testing the ethanol and finding out that it was considerably higher than 0.5%, but yet a child could come in and buy it. So, there's some legality issues here that need to be dealt with. So that's a big test component of kombucha manufacturing, is determining how much ethanol is in the kombucha. So the next lab we're going to do is actually going to involve exactly that. We're going to take the very same kombucha samples that we looked at this week. And if there's enough left, we're going to come back around and we're going to actually measure the amount of ethanol that's in the kombucha to see if it's actually legal for consumption or not. Okay, so that's the next place we're going to go. Oh, I didn't really want to select that. There we go. All right, so the next thing, and I'm really just going to be able to introduce it here, but we're still kind of continuing with the business of acids and bases. And what we want to talk about next are acid-base buffers. And probably your next homework assignment that I assign after the one that's due on Tuesday is probably going to be a buffer problem for you guys to work. And I might even get fancy and give every person a different buffer problem to do, just to keep it interesting. Sounds exciting, doesn't it? You're going, no,
Yeah.
not really.
A little bit.
Not really. All right, so when we're talking about an acid-base buffer, okay, we really have two definitions of a buffer. There's what I call the working definition. In other words, what does it do? And then I have what I like to call the chemical definition of the buffer. In other words, what is it actually? What's it made up of? So let's start with the working definition. The working definition of a buffer is that it's actually a solution that's going to resist a change in pH if an external acid or base is added to the solution. So you might wonder, well, why would we care? I mean, why would this be something we'd want to do? Okay. And kind of the big area is biological work and biochemistry. Okay. So if you're doing biochemistry, you're working with biological molecules, right? So you're working with complex things like proteins or enzymes or things like that that have a very specific function. Okay. Now, here's the deal. An enzyme, for example, is a very, very specific protein that has a very specific job to do. As a matter of fact, all those reactions we were talking about above that the yeast and the bacteria and the kombucha do, those are all actually done by enzymes that are actually contained in those cells. Okay, so the enzymes are actually the, little catalysts inside the little chemical factories that the microbes happen to be. Those little cellular microbes happen to be. Okay. So it's really the enzymes that actually make the reactions happen. And they happen very, very specifically. And that specificity comes about because of the actual three-dimensional structure of the enzyme. And we'll talk about this later because we actually have an enzyme lab that we do later in the semester. But here's the deal. Enzymes, of course, are meant to work at physiological pH. That's the pH of the human body, for example. So if I'm harvesting enzymes out of human cells, right? Well, those enzymes are really only going to be active over a very, very narrow range of pH that corresponds to your physiological pH, which is somewhere around like what, 7.4 or something like that. Does anybody know what it is?
I don't know the exact
little-
number, but I know it's about 7.
Yeah, it's a little bit north of 7. So it's slightly basic. Okay. I think it's around 7.4, but I could be wrong about that. So if you get an enzyme into a solution that's a little bit too basic or a little bit too acidic, what ends up happening is the enzyme actually denatures, which means that it changes its three-dimensional structure. And when it changes its three-dimensional structure, it can't do its job anymore. So the reaction basically stops. So here's the, the question I always ask in every quant class or even in dynamics, I always ask people, I say, well, what happens to you if like your pH in your body goes too acidic or too basic? Anybody know?
Death.
Yeah, you fucking die. That's pretty much what happens, So that's the situation. So this is why this is really important. If you're going to basically study these enzymes or any other biological molecule that has a very specific function, you have to keep it at a very, very narrow range of pH, even though you might be doing all sorts of chemistry with it that might affect the acidity or the basicity of the solution that it's in. So in order to do that, what we do is we actually buffer the solution to that pH so that if we do add other components that might change the pH, okay, now that solution will resist that change in pH so the enzyme can still continue to function. So that's what the working definition of the buffer is, and that's where they're primarily used. It's not the only use for them, but it's a very huge use. Now, how about a chemical definition before we head home? Well, the chemical definition is basically what the buffer consists of. So it's an aqueous mixture of a large excess of a conjugate acid-base pair. That's all it is, okay? When I say a large excess, I mean it's going to be there in a much higher concentration than anything else that we're going to add to the solution that might do chemistry, right? So we want it to be there in, a 10-fold or 100-fold excess concentration. Because otherwise what happens is we would overcome the buffer and we would lose control of the pH. But basically, we know what a conjugate acid-base pair is, right? Conjugate acid-base pair could be something as simple as this. It could be ammonium and ammonia. So I can make a buffer out of an ammonium salt combined with some liquid ammonia. Another example might be this. acetic acid and its conjugate base, which is, oh, guess what? The acetate ion. And I could introduce that into the solution, for example, as a salt, like potassium acetate or sodium acetate, something like that. So that's essentially all a buffer is. So what we're going to do next time, guys, is we're going to come back and we're actually going to talk more about actually how a buffer does its job, why it actually buffers pH to a specific range of values. And then we'll actually talk about some problems we can work involving buffers. Okay, any questions or comments for today?
Something fun. I was looking up kombucha, the etymology of the word. So it comes from the Japanese word kombu, which is kelp, and then cha, which is tea. So it's somewhere
Kelp tea.
along. Yeah, but that's not what it is. So somewhere along the line in translation to English got screwed up. The N in kon got replaced with an M. And so the definition also changed.
Okay, makes sense. And a lot of people actually call it, interesting enough, they call it fungus tea. And everybody goes, ooh, it's got fungus in it. And I think that's because of that mushroom-like SCOBY that actually grows on top of it that looks like a big mushroom cap. But in fact, it's just a big cellulose membrane that, like I said, contains the microbes. But there's no fungus whatsoever in it. So when you hear it called fungus tea, it has nothing to do with fungus. I actually caught Dr. Freely on that. He actually thought there was fungus in it. I was like, no, there's no fungus in it. It's just called that because it looks like a big mushroom cap on top. So all kinds of good, interesting stuff about kombucha. All right, guys, I will see you on Monday then. And work on your homework. Remember, you got a homework assignment that's due Tuesday.
Have a good day.
All right, you guys too.
Have a good one.
Thank you.